we have not started. So there is no
Thank
noise,
you, ma'am.
sound as such.
It's okay, ma'am. कोई बात नहीं. Thank you.
Neha, you can start recording also.
Yes, sir. I have already started.
Miss Neha, please can you turn on the chat?
Hello, Nihadi, there is a request to turn on the chat. So if it is possible, if that can be enabled.
See, I have done that, Saptarshi. See, check if it is.
Yes, it is enabled now. Yes, it is
Okay.
enabled.
Thank you, ma'am. So nice of you.
Sapna, you may start now.
Yes, yes. Very good evening to everyone. I, Sapna Ramani, Strategic Lead of S4DS, on behalf of Society for Data Science, welcome you all in its webinar series. Before we begin with today's session, let me share with you brief about Society for Data Science. Society for Data Science has been founded in January 2018 by a few data scientists and data science enthusiasts from various parts of our country, with an objective to create seamless data science ecosystem, and it is growing rapidly with every single day. S4DS is basically a non-profit professional association to create a collaborative platform for bringing together technical experts across industry, academia, government labs, and professional bodies to promote innovation around data science. S4DS is committed to serve members, improving the data science profession, eliminating bias, and enhancing diversity and advancing ethical data science throughout the world. It offers various activities. Few of them are workshop, webinars, panel discussions, projects, hackathon, research work, and the flagship event of S4DS is International Conference, which is upcoming event in January 2021. With the same line, today we have another feather in its webinar series by Professor Philip Bradford. Here are few glimpses. Here are few glimpses of the earlier conducted webinars by academia and corporates from University of India and abroad, from the industry like IBM, TCS, Apollonis. Participants can watch our YouTube channel for the detailed content of the webinars. Now, the moment for which we all have assembled today. We have amongst us today Dr. Philip G. Bradford to add one more feather in its webinar series. It is my pleasure to introduce Dr. Philip. Dr. Philip G. Bradford is on the faculty at the University of Connecticut. He is the director of the computer science program at the University of Connecticut in Stamford. He is a computer scientist with extensive experience in academia and industry. Phil was a postdoctoral fellow at the Max Planck Institute for Informatics. He earned his PhD at Indiana University, an MS from the University of Kansas, and a BA from Rutgers University. He was on the faculty at the Rutgers Business School at the University of Alabama's Engineering School. He worked for the BlackRock, Reuters Analytics, founded a startup and worked with a number of early stage firms. He was a principal architect for General Electric. Phil has a deep belief in bringing real research to practice. This is the root of his entrepreneurial perspective. Phil has a handful of best-in-class results. His Errod's number is 2. His Errod's number is 2. That's what I announced, that today we have expert of mathematician with us. He has given over 70 talks in 9 countries, and he is the author and co-author of over 65 articles. Sir, we welcome you all. We welcome you,
Thank you.
Dr. Philip.
Thank you very much.
Thank you, sir, for being with us today. And over to you, sir, today's session.
Oh, thank you. I'm going to share my screen if that's okay.
Yes, yes, sir. You will share.
Okay, let me see. Whiteboard desktop, Microsoft PowerPoint. How about, oops. Let me just do this. Yes. Let me just open my system preferences to allow Zoom. Oh no. It says I have to quit Zoom to record. Let me do that later. Let me see if I can, let me just see if I can, you can see my screen.
Perfect.
Yes, sir. We can see, sir. Yes.
Okay, good. And you're recording? Perfect.
Yeah.
Okay, let me put this up here like this. Can you see the whole screen?
Yes.
Okay, well, first of all, this is a great honor and distinct privilege. And I want to thank Dr. Sharma and Dr. Saha for inviting me to this wonderful event. So today I'm going to conclude with context-free graph querying and why it's useful in large data sets with applications of data science. But what I really want to give is a perspective on data science, and I'm hoping that my perspective will enhance people's thinking. Some of this may be common knowledge among some of you in data science, but I'm hoping that I can trigger some more thinking in it. And then we'll move on from there to how graphs are a natural extension of a lot of data science. And then we'll look at how people have started ordering, adding labels to these graphs, and particularly interested in causality in data science. And looking forward, I think this could lead to some nice research. And I'm particularly interested if anybody sees some good applications, and I think there are some out there already, I'm eyeing that we could apply this research to. So the first thing I want to talk about is the late Jim Gray, who was a Turing Award winner actually, but he talked about the data-driven data science being the fourth science paradigm. So he viewed all of science as starting with the empirical science, was chemistry and physics. The classical, we have an experiment. Most experiments really can prove things that don't happen, not prove that things are absolutely true, but in their context, we know things are true. And empirical science has played a great role and has had a terrific number of applications. In the classic sciences, chemistry and physics are two great examples, psychology and a bunch of others. Then they're moved to theoretical sciences, and this is where we started building more sophisticated models. And you could argue this is more in physics and chemistry as well, where we could get some ideas of what's going on under the hood. We had a model, for example, of the atom and of the different layers of the electrons. And these theoretical models sometimes got quite sophisticated mathematically, but were very good. And then we jumped to the third paradigm of science that Jim Gray was talking about, was the computational sciences. And here, for example, we have leveraged computation. In statistics, we might look at the bootstrap or jackknife, and these ideas were that we can use computation to enhance our abilities to understand and generate more data. In addition, with computational modeling, we could do some nice calculations. And finally, Jim said we have the data-driven models. And so here in the data-driven, there's really 4 areas that many people break out: descriptive, proactive, predictive, and prescriptive. And the descriptive is quite interesting and classical. So in descriptive modeling in data science, and I'll put this as a part of data science, but descriptive is classical statistics. And what I mean by that is we would determine which distribution is being followed by a particular process, or we might decide which data set belongs to a particular distribution. That's very descriptive, very important. And the big tools in descriptive modeling, which does not really grasp data science in a way, and is almost an antithesis of data science, is in descriptive modeling of data. We often, one of the key goals is to find a viable sample of a large population, where this viable sample has all the attributes of the population. And of course, that's the antithesis of data science, because data science says, okay, you have a great sample, you're done. You know, if you can find one. Data science wants to find more subtleties and things that actually are more subtle and in fact can have a profound impact that maybe don't follow the typical sample. Okay, then in data science, there's the proactive data science, and this is anticipating change. In anticipating change, for the proactive data science, we might do things like simple statistical models. And we might say, well, this particular drug is starting to wear off its effectiveness, and you know, things are changing there. We might also proactively model things that are good and bad. In proactive modeling, for example, I would characterize the notions of products and services as we model those. Then there's predictive driven data science. And here's where we're trying to predict what will happen. This is a lot of machine learning and a lot of things that are pretty important in data science. And so we really want to see not just what's happened, not just what distributions things belong to, not just preparing for anticipating change, but actually predict what will happen. And then we can work with that. And then there's prescriptive. Okay, prescriptive is, how do we handle these things that are coming along, and how do we even understand how they're caused? And prescriptive to me is, in much of data science, we can look for cause and then effect. And just understanding the effect can be descriptive, can be proactive, even predictive. But if we understand the cause, the root cause particularly, sometimes we can enhance our ability to act in science. And so I think that these 4 categories are often discussed in data science, and I think they fit beautifully well. So there's some very important people in understanding data-driven science. And so I go back into all these famous folks. Carl Pearson, who is famous for his correlation, and that is very descriptive. Okay, so correlation describes the type of, how data is related to other, one set of data is related to other, or how things work this way, and that's very important. We have proactive work in data science, and Abraham Wald looked at sequential analysis. That is, if we have 2 streams of data coming in, do we know that these streams are representing the same process, or are they distinctly different processes? And we'll talk about that a little bit too. And then there's Debarata Basu, and he famously was in Calcutta at the Indian Statistical Institute. He actually did some wonderful work that I think tells us about maximum likelihood estimators that we'll discuss, and that in particular his ancillary statistics and his insights there were very important. And then we have Judea Pearl, who really did a lot of work in prescriptive causality. And so Judea Pearl's work here is something I think we can also look at and follow up on. So in descriptive data science, we know that we have this chi-squared distribution. This goes back to Gossett, and Carl Pearson built some statistical tests on it. And there was some wonderful, very simple but beautiful observations. So Carl Pearson, Pearson both, as well as before him Gossett, published it as students, said, okay, if you're looking at the sample standard deviation, we square a bunch of terms, we get their square roots, but squaring the terms is going to make them all positive. Because anytime we square a real number, we're going to get a positive number, and we get rid of any negatives. And so he had this interesting observation, and very nice observation. His proof in Gossett's original paper under student was nice, but I think later on it was really improved by Basu in understanding how to show that there's independence between the sample standard deviation and the sample mean, and in a deep way. But descriptive statistics was very important, and this was actually had a very interesting application. It turned out Gossett was hired by the big brewing company in Ireland, Guinness, to understand the quality and do quality assurance for the inputs to making their beer. Okay, so a very important process, but this is very descriptive and very beautiful. I'm not taking away from the fact that it's descriptive. I'm not saying descriptive is weak or bad. It's a key lever that we need to handle. Then there's this notion of the proactiveness. And there's this idea, so we have standard tests, some hypothesis testing and things that go way back to Pearson and before. And Abraham Wald said, and independently Barnard said, we can actually have two data streams coming in, or multiple data streams. And we might ask the question, as these data comes in, are we changing our hypothesis, or are we converging to one hypothesis or another? Are we, we have to be careful of the probability of rejecting a true hypothesis, and we have to be careful of the probability of rejecting a false hypothesis. And so he did some simple transformations, and he built a stopping rule. And these RNO ratios of the different statistics coming in two different streams, actually the logarithm of the ratios. And what Wald did was quite interesting at a very high level. Wald said, he proved actually if these are different distributions, eventually this stopping rule will converge and tell us that they're different distributions with probability 1. The same distribution, likewise, eventually the stopping rule with probability 1 will tell us that we actually can tell, the hypothesis test will tell us they're different distributions. And I think this is a very important idea, being proactive and being able to anticipate change and deal with change and watch things as they change. So this is quite nice. Then we have the predictive, and the predictive is, of course, challenging. Predicting the future is hard, certainly. And one of the more famous tools we use this, and this is becoming a big important piece in machine learning in data science, is maximum likelihood estimators. In particular, we're looking for what parameters can give my model better results, okay? And this can change as the data gets much bigger, et cetera, et cetera. And this hits at the root of, Bayesian analysis versus descriptive or frequentist analysis. In particular, we have the a priori, as many of you know, views of things, and that we have these distributions that we have prior knowledge of, and our objective is to discern or even to test if new data points belong to these distributions, or we have a new distribution coming along. And of course, a posteriori, we're looking back, and in effect, we are saying, well, we're going to depend on our previous statistical tests to their outcomes to determine new outcomes that may or may not be true. Because our old statistical tests certainly could have been 95% accurate or even 99% accurate, but that's not 100%. And so our posteriori thinking is a different level, and there are people who think that maybe it's a little bit risky here. In particular, we can say some event occurs given the hypothesis, and this is, of course, a reversal. This is a Bayesian thinking. That is, did an event occur given that the hypothesis is there? Now, that's kind of the reverse of saying I have an hypothesis, what's the probability of an event? And so this is actually equals these probabilities of the probabilities of, this is the inverse statistics here, the probabilities of the hypothesis given different events, given the probabilities of the hypothesis holding true, et cetera, et cetera. And this can be approximated sometimes with maximum likelihood estimators simply as the probability of the hypothesis given these two different events. That is, the posterior probability equals the likelihood times higher divided by the evidence. And this is predictive, which is tricky. And so we're even using trickiness with this. And so this leads to very important things, in particular in predictiveness. So if we have a distribution or a data set, a parameter is a distribution of the entire population, as all of you know, I suppose. And the statistic is a description of a sample. So we may have a nice sample, and if ideally we're looking for a sample fully represented, not quite data science. Data science, I think, goes beyond that. But this is a good foundation for data science. Okay, so Fisher described an ancillary statistics that is a description independent of the parameters of the population, which is kind of a remarkable idea. So, for example, the sample mean relates to a population mean. Okay, it's not the population mean; it's the sample mean, but it relates to it. So, if the population mean is 17, then a lot of samples will be close to that, hopefully. The sample variance is ancillary to the sample mean because it's independent of the sample mean. In fact, the sample variance is distributed by like chi-squared. And so you can imagine we might have a sample mean that's 17, but we can have a giant spread, okay, or we can have a tiny spread. Okay, that's the variance can be giant or tiny. We can still have a sample mean and the population mean of 17. And this is where Deborah Basu showed some wonderful work. In particular, he showed that when looking at maximum likelihood estimators, there's no unique maximal ancillary statistic. That is to say, you might say, look, I want to get a great estimator of this model, and this estimator, I want to make it really a tight estimator. It'll do really well every time. Well, Basu proved, and in fact gave several really good arguments on this regard with his proofs, that there is no unique maximal ancillary statistical measure. And in a certain way, you might say, well, that means data scientists will always be employed. Okay, so we have to experiment with our maximum likelihood estimators. And the maximum likelihood estimators often have some assumptions anyway that make it challenging. For example, they assume, at least the generic ones typically assume, that everything that occurred before occurred with uniform probability or normal probability, if you wish. And so there are some big assumptions there, which gets into the Bayesian reasoning. That is, we're assuming something in the past, experiments in the past actually give us some validity to go forward, look into the future. But Basu even showed there's no ideal statistic that's independent from the population statistics, which is a pretty deep idea. Now, I want to talk a little bit about prescriptive. And I think prescriptive data science relies a good deal on causality, or causality is going to be very important for descriptive data science, for prescriptive data science. And so in some literature, like in the philosophy literature, there's something called the Reichenbach principle. It says, if A and B have a common underlying cause, and the probability of A and B occurring is bigger than the probability of the two. Okay, of course, the probability of A and B equals the probability of A times the probability of B, we call A and B independent. Okay, if the probability of A and B is less than the probability of A times B, then we might call them anti-correlating. Okay, or maybe A diminishes the likelihood of B. But here, since A and B is larger than the of A and B, we might say that A and B have some common cause. And one of the people that worked a lot in this area is Judea Pearl, and he built Bayesian graphs to describe this. Okay. And this is an example of Pearl's here. He said if it's cloudy, he built a graph that looks like this. So it's cloudy, it's raining, the sidewalk was wet, therefore the sidewalk is slippery. And so the question is this causal relationship? It's cloudy, does that cause it to be raining? Well, no, but it makes it likely. And so or it makes it more likely than if there's no clouds in the sky. If it's raining, it makes it more likely that the sidewalk is wet, okay? And of course, if the sidewalk is wet, it makes it more likely that it is slippery. So we could look at a probability, we could evaluate the probability of these causal events as the probability that we have clouds and it's raining and the sidewalk is wet and it's slippery equals the probability of it having clouds times the probability of it raining given that we have clouds. So this is the probability of it rains given that we had clouds. And of course, the probability it rains that we have no clouds is going to be 0, but the probability it rains we have clouds, or cloud cover, is something positive. Then the probability that we have wet, the sidewalk is wet, given that it's raining, well, that seems like a pretty high probability generally. If it's raining, the sidewalk will be wet. But of course, perhaps that sidewalk is in the sun, and it's gotten very hot, and the rain just kind of gets burnt right off, so the sidewalk isn't even wet. So there is a probability that this is not the case, but this is probably a decent probability. And of course, once the sidewalk is wet, the probability of it being slippery, well, this could also vary depending on what's on the surface of the sidewalk. If there's sand on the surface, it's probably not going to be too slippery. If there's if the surface has been polished, maybe it will be very slippery. So Pearl gave this idea that we could take our Bayesian reasoning, in particular, looking at the common underlying causes, and actually have directionality with this and say, well, the sidewalk being slippery is dependent on whether it's wet, is dependent on whether it's raining, it's dependent on whether it's cloudy. On the other hand, the sidewalk could also be slippery simply because it was made of slippery rocks, or it could be slippery because somebody had spilled something on it earlier. So this is not necessarily the only cause of being slippery, but this is one pathway of reasoning. And I think this is very important because it gives us, even though this, again, doesn't give us the full picture, it gives us a good portion of the picture. We may have many things that make a sidewalk slippery, But if we are looking at data science, one of our jobs is going to be to say what is one of the key causes of a sidewalk being slippery, and then can we prevent that? For example, if we see it's being cloudy and we know it's raining, how can we prevent, for example, cause preventing it from cloud is going to be an awful hard. That's going to be a difficult challenge. Preventing it from rain, well, we could put we could put umbrellas or cover over the sidewalk to prevent it from being wet. But there's each of these stages. As a data scientist, we might be able to go in and do some nice work in that regard. But now, doing this also, Pearl talks about generally, he has acyclic digraphs, not just linear graphs like the last one, and these get a little bit more complex. So, for example, the probability that we have a wet sidewalk, given that we have a sprinkler on and that it's raining, so we might have sprinkler and rain. Maybe the sprinkler and rain go on at the same time. It's possible. It may be a waste of resources, but that can happen. And so we can have these three, and this is acyclic, of course. This is the probability of it being wet given the sprinklers on and it's raining. Okay, so both of the sprinkler being on directly affects the wetness, and the raining directly affects wetness. However, this is affected by the raining. Ideally, don't put the sprinkler on when it's raining. So this might even be a repression of this sprinkler being on. So this is not necessarily a Reichenbach condition. This is the opposite. We want to suppress the idea that the sprinkler is on when it's raining. And of course, this is the probability simply of it being raining. And these basic acyclic networks, or Bayesian acyclic networks, actually, we compute things in them. As an example, if we have two nodes in a Bayesian acyclic network, they cannot reach each other. So if we have a node A and a node B, A can never get to B and B can never get to A, then they're independent by definition. This also led to a great idea that Pearl talks about and that he gave. In particular, he talked about experimenting in these graphs. So once you have a graph describing these different phenomenon, you can say, well, let me just, if I want to see if the sidewalk is wet, I can just spray with a hose and see if it could be wet without, when water gets on it. And so he would have the do operator, and the do operator says, let's do an experiment, and then let's try to run this thing. And that gives you evidence towards causality, and which is a great idea of this, and just very clever. And in a way, that's perhaps an ideal thing to think about in terms of causality. Let's do an experiment and try to push things over. And as a data scientist, that's very important. In some cases, it may be very hard to do, but in other cases, it may work out just fine. And so it's quite an exciting area. And then I want to jump into the idea that we can take these basic Bayesian acyclic networks and we can expand them a bit. Okay, and what I mean by expanding the Bayesian networks is, first, this comes about in graph databases. There's a few of them out there. Oracle has a big graph database. Neo4j has a graph database. And but one of the early databases ever came along around 1970 and proposed a relational database. And the relational database, I bet everybody's familiar with. The relational databases are organized as tables, and the tables can have relationships among their columns as well as intertable relationships. One of the way I view relational databases is they're very much transaction oriented, which is extremely important for commerce and science and engineering. I would even say for descriptive statistics, they record descriptive things. Okay, so if I go back to the models we were looking at earlier that Jim Gray pointed out, I look at relational databases as very descriptive. Now, of course, they can be used to predict, and they can be used in many, many ways. But the question becomes, what is their nature, and what are they probably most targeted to? And I would argue they're transaction-oriented and they're descriptive-oriented. They want to just, what I think of a relational database, I think of who bought what, when, and how much did they pay, and et cetera, et cetera. Many other things we can do there. But then there became this notion of graph databases that's become more popular recently because of computing power and everything else. And graph databases are relationship oriented. In particular, we can define relationships in the graphs, and some of these relationships may actually not always occur. We may say here in this relational data flow here, we could say, this blue does business on Tuesdays with gold, but blue does business with green on Friday. et cetera, et cetera. So this graph, actually, we have some flexibility. And of course, with a graph, we can also even express things such as Bayesian networks from Perl, but we can also express labels on these graphs. And these labels can enhance what we're doing. So we could, for example, if we said what is going on Tuesdays, we could take our graph database and just look at edge labels that say this relationship occurs only on Tuesdays, and we have a subgraph all of a sudden of interest. The graph in general may in fact even be cyclic, but the subgraphs many of them may be acyclic. So we could have a key or Bayesian graphs that we can do computations with. And so this is kind of an important notion. And so what I'm going to talk about is context-free grammars labeling these graphs. And this is an area I've done some work in. So here's a basic context-free grammar. It's got parentheses. Okay, I have these open and closed parentheses. It's got a start symbol S. And I put the rules down here. The rules are these ellipses up here, which are these three rules. And the balanced parentheses so each parentheses either is doubled, we have a link here, or each set of balanced parentheses is either doubled, or it's wrapped up with the parentheses, or it is the empty parentheses. So for example, we can derive the nested parentheses here through this derivation of using these rules. We can even derive this parenthesization by just using the doubling, and then the doubling goes to this middle rule, and then we use the bottom rule, and keep using these rules and applying this. So we have this notion of balanced parentheses. Now, what I was interested in balanced parenthesization problems, looking at certain types of areas in understanding software and machines. Here's some counterexamples. Here's some non-balanced parentheses. You can also, for certain non-balanced parentheses, of course, we can define formal grammars and even context-free grammars if they're well enough formed. But these are not, in our world, in my world, these are not balanced parenthesizations. I just want ones that are typically of mathematical expressions. And what particularly I want to look at is if we have a graph, we can label its edges with, in general, we can label with context-free grammars, or in particular, we could label with balanced parenthesizations. So if you take this graph here, and we start from node 1, 1, and we go to node 4, 4, let's suppose we require that we always begin in node 1, 1, and we always end in node 4, 4. When we go through this graph, any path in this graph, we're going to end up with a balanced parenthesization, because each time we go to the right here, we're opening a parentheses, and each time we go down, we're closing. But this gives us all possible, even imbalanced parenthesizations. Here's open, 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 close, close, close. This is not right, not a balanced one, but above the diagonal, we have all of our well-formed parenthesizations. So above the diagonal, we have all of parenthesizations defined by this rules. Below the diagonal, we have all ill-formed parenthesizations. So we might have the rule that we only can go above the diagonal to get from 1, 1 to 1, 4, which is fine. And this may actually give us some insights into data science in one way or another. In particular, in prescriptive work, we often do here in natural language, and this is particularly Griffin and Tenenbaum talk about this. We talk about a graph like this. We'd have a behavior. So if somebody has a particular behavior, they're limping. Okay, that's a physical behavior. That may describe a disease or a break or a sprain or something else. Okay, and that may cause another symptom, like they are late very often, or to getting somewhere because they have to hobble and walk. And this is just a typical Boolean network here, or a Bayesian network, which we might go back to some of Judea Pearl's work with that, which could be very nice. But also, we can and what Griffiths and Tenenbaum talk about is we can probably large networks of nodes with labeled edges, and these edges are labeled in their context with probabilistic graph grammars, context-free grammars. And we might have something like this. We might have a gene A and medication 1 and gene B. So medication gene A has certain effects on the state of the organism. There's certain side effects with medication 1 in this case, and they maybe make state 1 not ideal, and this could be linked to longevity or counter-linked to not walking as much, okay? Likewise, medication 1 on gene B could actually have some effects where gene B gives us side effects instead of effects. So we have state 2. This gives an indicator that we will be walking a lot, so this will encourage us to walk. And so the arguments that Griffiths and Tenenbaum give service to build, use probabilistic graph grammars to build sophisticated graphs and to describe these things. And many times in natural language or in our description of causality itself is a grammar. And in describing these grammars, we can actually compute and find subtleties in these grammars. So if somebody has a subtlety that they're looking for, we might be able to look for it and in fact enhance some of our understanding of causality in doing so. And so as a conclusion, data science is a paradigm shift. Going back to Jim Gray, it is maybe the natural next stage. We can store huge amounts of data. We can sift through giant amounts of data. We can use our other tools for frequentist statistics or descriptive statistics, proactive modeling. We can use predictive modeling, max likelihood estimators, and all these really good things. And then we can also use causality. I think causality is a really big deal in prescriptive statistics or prescriptive data science. That is, not only do we want to understand where we have those gems and where those great ideas are that we want to execute, but we want to understand why those things occur. Because once we understand why or what the causes are, then we can really earn our keep as great scientists. And so these new tools like this, like causality, I think will keep adding great values and open up new areas. Okay, and so what I'm looking at, and I think Dr. Saha and I have looked at this a little bit. We're going to maybe dive a little deeper. Is looking at labeled graphs to augment causality, and causality actually is a very hard thing. Even quality compared to descriptive statistics. In descriptive statistics, we often hear the phrase correlation is not causation. Okay, very important phrase. Because correlation is not causation. Two things can happen to correlate, can be completely different processes, can be caused by completely different things. They just happen to occur at the same time. But if we understand causation as data scientists, we can really add a great deal of value. So that is my talk. Questions?
Sir, can I ask you one question?